my name is Dana Golden. Welcome to the first video in the cost-benefit analysis lecture. Cost-benefit analysis allows you to make informed decisions when faced with complex trade-offs. You have a variety of positives, a variety of negatives, a variety of costs, you have a variety of benefits. They're all coming at different time intervals. How do you make these choices? How do you come up with a solution to this problem? Cost-benefit analysis allows you to think systematically about this. It's a way of thinking seriously about the positive and negative actions, and often involves quantifying different types of costs and benefits and determining how to weigh them. It's not easy because you don't always have a good framework for how to weigh different types of costs and benefits, but it's extremely important in environmental economics. So one particular type of cost-benefit analysis, which is pretty common, is the economic impact analysis. And this evaluates the effects of a project, policy, or event on the economy of a specific sector or region. It measures the changes in key economic indicators such as employment, income, business revenue, and GDP. Its key components are direct impacts, which are the immediate impacts like jobs created by a construction project or revenue to the company, or revenue to the community rather. Indirect impacts, ripple effects through the supply chain, and then there are also induced impacts, which are the effects of increased income on local spending, such as more retail activity. There's some tools and techniques to deal with this, such as IMPLAM and RIMS2, which are input-output models, and you can also do econometric modeling and regional analysis. So some quick applications: you can evaluate infrastructure projects or assess the impact of local business investments or different types of policies using economic impact analysis. How will this impact the local economy? You're looking at here how many jobs are being created, what is the change in regional GDP or tax revenue, and what is the sector-specific economic growth. Then you have a regulatory impact analysis, and these analyses systematically evaluate the cost, benefits, and distributional effects of a proposed or existing regulation. It looks at whether or not the regulation is actually achieving its objective and whether or not it's doing it efficiently and equitably. Is there a way we can do this more efficiently, or a way we can do this that's more fair? So some key components: define the problem. What is this regulation trying to do? What happens if you don't have the regulation? And then how should you think about the costs and benefits? And then compare the potential regulatory and non-regulatory solutions. So tools and techniques: discounting for cost-benefit analysis allows you think about how the regulatory policy happens over time, because generally the benefits of regulation are more distributed over a longer time period. You can do sensitivity analysis for uncertainty. How sure are you of your assumptions? How likely is it that the industry will come up with ways around this regulation, or that you'll hinder innovation? And then you can do a distributional analysis for the equity impacts. So you can just evaluate environmental regulations, financial regulations, just about any regulation. Types of outputs you're putting out here are the net benefits of the regulations in dollars, the emissions reduction achieved, which you can then put into dollars by multiplying by the cost of CO2. And then you can look at the cost per life saved or per unit of pollution abated in the regulatory impact analysis. So this is a framework for the cost-benefit analysis. You start by specifying a project or a program, specification, location, timing, groups involved, connection to other programs. Then you describe the quantitative inputs and outputs of the program, typically monetary values. You say, here's what the program does, here's what the program takes in, here's how much it costs, here's what we could have done with the money, and then you look at the outputs and you try and put them in dollars. Then you estimate the social cost and benefits of these inputs and outputs. You determine the full range of consequences and compare the benefits and costs. One good framework for this is the marginal abatement curve, which represents the cost reducing one additional unit of pollution or greenhouse gas emissions. This is a graphical depiction of the cost of abating emissions on the y-axis and the cumulative amount of abatement on the x-axis. It is widely used to assess the cost effectiveness of different mitigation strategies. So it's generally upward sloping because it's a cost. So a mathematical explanation of a marginal abatement curve is the additional cost reducing emissions by 1 unit. So it's the derivative of the cost of emissions with respect to emissions and it's the marginal abatement cost of emissions. So the cost of emissions is the total cost of abatement for emissions E, and E is the emissions level after abatement. Marginal abatement curve is increasing in E, reflecting that reducing emissions become more expensive as cheaper options are utilized. And the curve integrates individual measures cost ordered from lowest to highest. On the other side, so that is the cost of abatements. That's analogous to a supply curve. That's a marginal cost curve. On the other side, interestingly, we have a marginal damage curve. It represents the additional damage caused by one more unit of pollution and greenhouse gas emissions. This is actually your benefit or your supply curve in our analysis. The curve is a graphical depiction of the damage caused by emissions on the y-axis and the quantity of emissions on the x-axis. So it's generally upward sloping, indicating the marginal damage increase with higher level emissions. It reflects the increased marginal damage done to environmental social systems, and this tends to be nonlinear. It tends to increase the more pollution you have because of the increasing effects of increasing emissions. And it represents externalities not captured in market prices. So here's a mathematical representation of that. Very similar. Marginal damage curve is you have a damage function, d of E. You take the derivative with respect to emissions, and you have the marginal damage of emissions. It increases with E due to the nonlinear effects of pollution. It reflects the environmental, health, and economic costs associated with emissions. Emissions. So here's how we can generally think about this in just a general cost-benefit terms. You have a marginal cost, marginal benefit. You set them equal to each other. Here's hours study before the economic test, and here's marginal benefit. So you have a certain number of hours, and then at 3, the marginal cost equals the marginal benefit. The benefit declines the more you study because there's less probability of you learning new material or remembering things. There's maybe a huge benefit to studying a little, and then that decreases. And then the marginal cost increases the more you study because it's harder to find those hours in the day, and because it's harder to focus for that long, and then that's equal to 3. And then you can equate the marginal damage and marginal abatement curves, which are analogous here. So here's the marginal damage curve, upward sloping in this case in terms of dollars in emissions. It's upward sloping because our emissions are bad. And then the marginal abatement curve, downward sloping, once again, because emissions are bad, they're not a good. So it's marginal damage curve. The more emissions you have, the more damage you do. The marginal abatement curve, the more emissions you have, the easier they are to abate. And so where they equal is right here at E star. And then the total benefits at E star are A plus, the total benefits at E2 rather, the total benefits of E star of that level of pollution is A plus D. So it's this. It's the area under the marginal damage curve by letting that happen. And so if you subtract out C and B, you get a net. You get the net benefits. So just problems in cost-benefit analysis. Who should get benefits and who should pay costs? You have horizontal equity. How does the policy impact similar people with similar incomes? You have vertical equity. How does the policy impact different people with different incomes? Higher costs matter more to a poor person, and people paying costs might be those might not be those receiving the benefits. We generally believe, as a society, that it's better for costs to be borne by those who have the greatest ability to pay. So we have person A, person B, person C. And then these are all very similar in terms of income. And then there's a reduced environmental damage for each of some amount of abatement cost. And then there's some difference. So the policy reduces person A's environmental damages, the cost to person A by $60, and then the abatement cost to achieve that reduction is $40, and the difference is $20. So if person C is receiving the greatest benefit, which is the highest level of reduced environmental damages, should they have to pay more for that? Should they have to pay more, given that there's a bigger difference between the reduced environmental damage and the abatement cost? Should this be equalized? And this is the question that has to be dealt with based on a philosophical definition of how we should deal with distributional questions. So, comparison with horizontal vertical equity. Equity refers to fairness in the distribution of resources, benefits, and costs. The two key concepts. Horizontal equity is equal treatment for equals, and vertical equity is differentiated treatment based on ability to pay or need. Vertical equity, you have three different people with three different incomes, and then you have you have three different programs which reduce damage for each of the people and have some amount of cost that each person must pay. The first one is making everyone pay the same amount, and actually the person who has the highest income has the highest level of reduced damages and the same abatement costs. So they have a big difference between their reduced damage and abatement cost is a big benefit to them, but it's even larger after you consider that it's a big portion of their income. And then in this next scheme, we have the person C. Person C experiences a much larger reduction in damages. Person A receives the same level of reduction in damages. Person B receives a larger reduction in damages. And then person C pays a much larger reduction in cost of abatement. Person B pays a larger cost of abatement, and person A remains the same in terms of cost of abatement. And then the third one, you have a large amount of reduction of damages for person A, who makes the least, and then you have a difference of 500, and then a policy for person B that has a difference of 1,200 between the reduced damage and the abatement cost, and then policy for person 3, there's a difference of 1,500. So in all three of these, you have a different level of difference for the person, how much they're putting in, how much they're getting out, and that has an effect that differs based on income. So horizontal equity is equal treatment of individuals with the same characteristics, ensures fairness amongst equals. Two individuals earning $50,000 should pay the same amount of taxes, and there's the idea that there should be uniform access to education and health care for similar people. It requires a clear definition of equality. And vertical equity requires differentiated treatment to account for differences in income, ability to pay, and need, and ensures fairness between different groups based on capacity or need. High-income individuals should pay a higher percentage of their income in taxes. And then this is means that social circumstances regressive taxation systems is the idea that if you've succeeded the most, you should contribute more. And this balances redistribution without discouraging economic productivity. So I'm going to stop here, and next time we'll pick this back up with risk valuation in the economic context and the environmental context. I hope you have a great day. Thank you, Dana.